Can you guys please confirm if you can actually see the slide? Are you guys able to see the slide? Okay. Perfect. All right. So last time, the last thing that we saw, we started with I'm gonna get there now. Okay, we're done talking about neural networks. Okay, and we got to image processing. All right, so we have image processing theories and applications. So that was what we started last week. If you missed the last lesson, please check on YouTube in the same playlist. You're going to find that lesson there. All right, so we will, when we talk about image processing, when we're dealing with any AI tool that has to do with image processing, so has to do with images, so that part is called computer vision. So computer vision is a part of AI that is focused on images, analyzing all the images and creating AI tools that have to do with images, right? So the way it works is that the computer has to perceive and understand a visual information similar to the way that human do it. So when we observe something, we look at different details about a picture, right, or a certain image, right? So we have the image recognition, image reconstruction, image reorganization. So we spoke about, and in this we said, in image recognition, the computer will have to take the image and convert it into an object. But in image reconstruction, it means we can take from pixel to pixel, from pixel to object in terms of image reorganization. And we've mentioned how computer vision is one of the core um, uh, field of AI. So in human eye imaging, so when we talk about human eye imaging concept in artificial intelligence, we are actually referring to AI systems that mimic or leverage human vision principles, like to process and understand visual information. So this will combine our computer vision, image processing, and neural networks to just simulate aspects of human visual perception. So if we have to look in a proper explanation, look at it. So this is inspired from the human eye. So the human eye actually works uh, as an imaging device, right? We have things such as the lenses, which will focus the light onto the retina. You have the retina that will have some cells, um, some cells that will detect the colors. Uh, you have optic nerves that can transmit visual signals to the brain, which will actually interpret shapes, colors, or any motion. So in AI, the goal is just to replicate the same idea, like from capturing the image, enhancing the image, extracting different features of that image, and making a decision by saying what does that image represent. That's exactly what the computer will also do. So we'll have a few concepts of AI that will be related to human eye imaging. So we have, for example, the image capture, right? And the pre-processing. So we have the camera sensors that will replace the retina of the human eye. So in the pre-processing stage, so we will have what we call normalization. like what the eye do to adapt to the light. So we basically, the eyes have to detect a light for you to see. That's why your eyes can still be open, your eyes can still be fine, but you cannot see in the dark because there is that absence of light. So your eyes cannot detect the light, they cannot see anything, right? So we're going to extract all the like the human brain can detect edges, shapes, textures, pattern automatically. AI will use CNN, use the layers in the CNN, so the convolutional neural network, to just simulate how the eye will detect edges, shapes, and all those things. But in AI, we use neural networks, right? So in neural networks, the early layers will just detect edges and certain pattern, right? And then other layers will just detect all the complex features like the faces, the objects, right? So we will have certain mechanism in computer vision that can really uh, help detect everything until we get to a point where we can take a decision and say this object represents a certain object. We can identify the object. All right. So we in computer vision we will have things such as the CNN, which is the convolutional neural network, which is a neural network that is used for image processing, right? And then so that is kind of imitating what the retina of a person does by detecting all the pattern, the shapes, and all these things. And then we can use as well generative networks such as the GAN. That's to just reconstruct some missing visual informations. And then we can also use transformers, like with ChatGPT, there's transformers. Okay. So when we look at the high will actually have to sense, right, something. So we have image sensing and acquisition. So the digital image is actually captured using process similar on how the eye functions. Uh, so the context of human eye in terms of AI. So we are actually looking on how visual data are captured and sensed and digitized for AI system. So in the human eye component, we have like the lenses, which will actually as a function to focus light onto the retina. But in AI, we have camera lenses and optics, right? So we have different part of the eye, and in AI we also have those. So the image acquisition process will really involve emerging the input electrical energy with photoreceptive sensor material, which will convert that input energy into voltage, then sampling and quantifying the results wave to just obtain the discrete image, right? So we have image sensors, we have color sensing as well, which will actually detect what's the color in the image. We have an image acquisition process, right? Where we're going to capture the light through the lenses, and the sensors will detect and get the color pixels, converts that into a signal, right? And then we can actually process that image and identify the image. All right. Um, so now we have these lenses and the retinas that are playing that role. And then we have what we call image um, digitization. So when we talk about image digitization, so this is just a step, um, the same way with the human eye concept, right? So in this case now with the AI, this will be just a process of converting the real world visual information which is the light, into a digital format that the AI system can process. Okay, so this process will just be converting the optical image from whatever environment that we get, the camera, into matrix of numbers, which we're going to call pixels. Right, so this image is taken into, converted into matrix numbers. So each pixel will represent a small portion of the image. Remember when we spoke about how we're going to use in a neural network, we're going to use the first layer will be the input layer, which will have information about each pixel. So that's what it means. So when you look at this whole image here, in AI, we're going to identify this image based on each pixel. So each pixel represents a small portion of the image. So each pixel has a numerical value, which is corresponding to the intensity, brightness, and color. So this is how AI can identify this logo, for example. You look at this pixel here at the corner, it's too light, so there will be a value to that, like a numerical value to that. This one is too dark. There will be each pixel will have a numerical value corresponding to the intensity or the brightness or the color. All right. So the digitized image can then be processed and analyzed by the AI algorithm. You understand that? So whenever we take an image into the AI is not going to understand this image until the image is digitized. So for the image to be digitized, it needs to be, each pixel needs to be given a value, a numerical value. All right. So, so the steps will be the image is first sensed, right? So the sensors will sense the image, and then the image will have an analog to digital conversion of the images in terms of the voltage taken into this conversion, and detect the color. So there will need to be color encoding. Each pixel will have 3 channels. We have what we call the RGB model. We're going to talk about it today. The RGB model will have 3 colors: the red, green, and blue. All right. And then we can have other models such as HSV lab and other coloring encoding. And then we're going to have kind of a sampling and quantization. So when we talk about sampling, that means we're going to determine what's the spatial sampling. So how many, the numbers of pixels in terms of the image resolution. So how many pixels does this picture have, right? So, and then we have quantization, which means that we're going to assign a numerical value for the intensity or the light or the color of those images. Okay, that means that we will have, for example, we have a 256 level, which can have 8 bits, you understand? So that's how the image will be digitized. Okay, and then from there now we're going to move to sampling. So sampling is just a fundamental concept of the whole digitization process in AI, which is similar to how human can capture a certain detail of a certain scene. So this is the process of just measuring the image signal, right? We are actually measuring the image signal in order for us to create that digital representation of the image. So in analog images, like what the human eye can perceive, the scene is just continuous. We just don't have details about that. But to digitize it, we sample points across the image to form kind of a grid That exactly. So in that grid, each part of the picture, each small portion of the picture will have a detail about that pixel. So we have uh, the density of the sampling itself will determine the resolution of the picture. That's why they will tell you, this image is high resolution image or low resolution. You take a picture with an iPhone 16, and then you take a picture with an iPhone 6, you can see you took the picture of the same thing, but you can see there is a low resolution and an high resolution. You can see that is the process of sampling, how the computer is actually, or the phone in that case, is actually understanding these images. All right, so the resolution of a discrete image is determined by its size. All right, so that's how you can see when you look at the camera, you're looking over, this is a 50 megapixel, this is a 20 megapixel. So this is what we're talking about here. So that is a spatial sampling. So that refers to how the image is divided into pixels. So each pixel will capture the intensity and the color at a certain location. So the higher spatial sampling we have, the more pixel, the higher resolution, the more details. Do you understand that, guys? Do you understand that, guys?
Sir, can you please repeat that?
All right. So we'll compare these two. When you look at an image, you have the resolution of the image. You can see it. They tell you the size of the image. You have a 640 by 480, which is made up of 307,000 only point. But when you look at this image with this resolution, this will be made of 2 million point. All right. So this is why you find you taking you're looking at a camera, or you take your phone, just take two phones and check information about the camera. You see that, okay, there's a camera for 50 megapixel, camera for 20 megapixel. You can see the 50 megapixel, the quality of the images is good. What does that mean? It means that that image, when you take an image, it take detail, it take more details. Think of it as a grid. A grid, we have a grid like we've shown it in this, which slide was that? Uh, we have it in this. So you take a picture. So this picture needs to be divided into a grid, and the camera needs to get details about each box. So a low resolution picture will mean that there's less grid, there's less points taken into account. But when you take more points, it has more details. So the higher the spatial, the sampling, the more pixel, the higher the resolution, the more details we have of the picture. All right, so that's exactly what sampling will do. So because we need to take all the picture, the colors as well, need to get information about the colors. All right, so when we're looking at why sampling is very important, it's because when you look at AI models such as your CNN, the CNN will rely on the pixels values to detect images. All right, because the first layer, which is the input layer, will have to take information about death. You understand? So if you look at these two images here, can you see here we have S node in the input layer. Here we're going to have more. So we have more information here than we have. All right. So when we're looking at cases where we will need to look at it, because when we have a higher sampling, it means we have more data, we have more computation, of course, but then our AI is going to be really good because we have more details. All right. So from sampling, so when we're digitizing the picture, we have sampling and we have quantization. Quantization. So when we talk about okay, these are examples of pictures. Can you see this is 1,000 by 1,000? This is how it can look, 350. So the more, the less we're going, the less details we have over on the picture. So when we talk about quantization in digital image processing, so this is just the process of converting the sensor signals into discrete integers values. So what does it mean? So this is the next crucial step after sampling in the image digitization process. So this will actually so in this process after the sampling, so what's going to happen is that each pixel will correspond to a specific location in the image, right? So quantization will assign each pixel with a numeric value which will represent the intensity or the brightness or the color of that image. So this is how we can be able to use it in a neural network. Those are the values that are going to be there in the first layer. These colors or intensity, you understand? So this is how the image will be. So these values, like this intensity will be converted into values. So how this quantization will work is that we're going to have an example. We have, for example, the light that is hitting the sensor might produce maybe a voltage of 0.4 volt. So now quantization will just map this value into the nearest available level. So for example, we have an 8-bit quantization, which has 256 levels. Okay, so an 8-bit image indicates that each sampling point is that, right? So for 8 bits quantization, so we have 256 levels. That means that if the voltage that was taken by the sensor for that part of the image was maybe 0.4 volt, that may be mapped to maybe level 117. Okay, so so now the bits that we're getting, so we have 256 level from the darkest to the brightest level. So that's how it's going to be mapped there. Okay, so this is what we're going to have. So if for example, we were dealing with a 12-bit, so in the 12-bit images, we're going to have about 2 to the power 12, which will be 4,096 levels. If we were playing with a 16-bit, so it means we will have 2 to the power 16, which will give us 65,536 levels. So the higher bit depth, more precise representation of the intensity, and less loss of the details. All right, so now in terms of quantifying the colors, in terms of quantifying the colors, we have a color quantization. So for color images, the quantization happen per channel. Remember now, when the picture is black and white, the quantization just has to do with the intensity only. But if the picture has a color, we need to also look at the color channel. We have what we call the RGB model. The RGB models mean that we have a red, green, and blue, right? So each channel we quantize separately. So we're going to have maybe the red. So red as well, we're going to have maybe 8 bits. That means we're going to have 256 levels of the color red, 256 level of the color green. You understand? So that's how it's going to be. So each level will be quantified. So by the time we can get all the colors, we're going to combine everything. All right. So so when we look at the color images there. So first, this is the quantization effect. And then these are just how the calculations are going to be done. These are the pixels. So each pixel will have the information there. This is how the storage of this image, for example. So if we can look at it, I'm not sure if I can be able to zoom. Can you see? So each pixel will have its quantity. And you see, this is maybe 255, 255, and so each image. Can you see where we have the logo of the Huawei Day? Can you see the numbers are different? So each images will be. So in this case, for example, we given the bigger number, the highest level to the white color. So from white to darker, that's how we are actually going. Okay, is there anybody who doesn't understand this part? Can you see when I'm zooming? Can you see? You can actually see that that picture there. So each pixel in that case will have that. All right. Can anybody tell me without counting, how many numbers do you have there on top there, from here to here? Can anybody tell that? Without even to count.
30.
Yes, we have 30. So this image is a 30. So now each part will be given a certain value. You understand? Each part will be given a certain value. So now, if you creating a neural network, it means each of these number will be in the neural network. Can anybody tell us how many nodes are we going to have in the first layer? How many nodes are we going to have in the first layer? Can anybody tell us? How many nodes are we going to have in the first layer of our neural network? Guys, that is simple. How many of these numbers do we have? How many of them do we have? How many of them? Guys, this is a simple question. Guys, how many of them? Is there anybody who doesn't know how many of them? Or is there anybody who doesn't know how to get the numbers?
Sir,
Yes.
is it not 900?
Yes, it is 900. Because we have 30 here, 30 down. That is 900. Where is the 30 coming from? It's right here. That's the size of the picture that we were given. It was a 30 by 30. So we have 900 this side, 30 this side, 30. The total will be 900. So we will have 900 node in the input layer, and each node will take this information as the numerical number. So now, if this picture was in color, which means that now we don't represent it as this, like 255. Like here, we only have black and white. So we go from 255 to 0 based on how dark or based on the brightness. But if we have many colors, we were going to use the RGB model. So the RGB model, which stands for red, green, and blue. So each pixel in color images will be represented by 3 values. So the 3 values will correspond to the intensity of red, green, and blue light. So now by combining these 3 channels in different intensity, we can reproduce millions of colors. This is how, when you are coding, for example, you want to put a certain color, you can mix, you will see maybe there is the color code is maybe 255, 24 something, and then we have 3 colors. It means it's the intensity of red and green and black. So by changing these intensities, you can create as many colors as possible. So do you understand how our computers, our cameras understand colors? They don't look at blue, black, or no. They take red, green, and blue. They take these colors, which will actually be mixing. So they will mix these colors by changing these numbers and creating other colors. All right. So understand that black will be a 0, white will be a 255. In this case here. Now, if we have colors, the image will actually be represented by the color image model. So in this case, we're going to have this sign. So this will indicate a pure red. So we have an example of this. So when you look at this, there is a mixture of a bit of red and other colors. So this will represent long green, sky blue. So you see, so this is how the RGB model is going to work by combining these 3 channels of red, green, and blue. So by combining these 3 channels, we can obtain millions of colors. Okay. All right, so that's how the computer is going to identify that. And then other color images can be model can be, we have the HSV. So the color images in HSV are just another way of representing color in digital imaging in AI. So basically, HSV will stand for U, saturation, and value. So that is U, saturation, and value, which will just measure the degree and ranges from 0 to 360. So the U here would actually represent the type of colors. So we have red, green, blue, and others, and then which is measured from an angle of 0 to 360 degree on a color wheel, right? So this is how it's going to be measured. So, and then the saturation, which is the S, the saturation would represent actually the intensity of or the purity of the color. So for example, we have 0%, which will be a gray, 100%, it will be a full color, you understand? And then we have the V, which will represent the brightness. So the V represents the brightness or the lightness of the color. Okay, so HSV, so when we talk about the brightness, we have a 0, which is the black, and 100, which will be the full brightness. So you can see this in many systems where you can see where they are using actually the color wheel to just see how you can do that. You've seen that in many softwares they are using the HSV model. Okay, so this is how the HSV will work. So why is it really important in AI? Because it's really easy to separate objects by colors, ignoring the brightness variation. Example, if you want to do something like detecting red apples regardless of the lighting, because you see now, if you take a red apple, you change the lighting, it can be detected in AI, it can be detected as a different color. So that can be kind of an issue there. So the HSV is very important because it can also consider the brightness and change in terms of percentages. So it has more details than the other system, the RGB. Okay. All right, guys. Any question? Any question? So other color spaces, we have the YUV, the CMYK, the lab, right? Which are different colors system that can also be used. So the colors we have a color space conversion because in computer vision, the algorithm related to color recognition, you understand? So when we have in the design of the algorithm related to color recognition, we have many colors that can work together, based on what we have. Those colors model, the HSV, the RGB, because you need to know that the HSV will actually separate the color type from color intensity. So you have like your saturation, your brightness, you understand? So remember, you have the color, the HSV, we have the color type, which is the U, we have the intensity, which is the S, right? And then, which is the S because it's the saturation. And then we have the brightness, which is considered to be the value. That's how we call it HSV. So that's what the HSV model does. So it separates the color type from the color intensity, brightness. So it's closer to the human perception more than the RGB, because remember, as humans, sometimes you look at something, despite the fact that the lighting in the room can be different, but you still identify something as the same. So you're looking at something that is pink, even if it's in the dark room, there's just a bit of light, you can still recognize it as pink. So human eyes can adapt themselves to the lights, the brightness, things like that. If you're looking at a certain car, even if it's parked under the shadow, you can easily say the color of the car. You understand? So when you look at the RGB models, it's gonna get lost there if there's a different lighting. Okay, so AI application use most of the time they use HSV model, for tasks like color detection, segmentation, or any type of recognition. All right. So, but these systems can work together by using certain formulas which are used behind the scenes when you are programming. So they use systems. All right. All right, guys. The whole for today. We will pick it up tomorrow. Any question before we can call it a day? All right, guys. Before we can call it a day, for those who can, you can turn on the camera so we can take the attendance. Because we still need to actually select